In this example, we will be building naive or estimating naive Bayes method. We will be using naive Bayes method to predict the probability that a record belongs to a particular class. So what does the question say? Studies have found that many companies plan to continue allowing their employees to work from home after COVID. Santiago Brown is the human resource manager of an international engineering firm. He has compiled the file about 200 employees who worked from home during the past year. The variables include whether performance rating of the employee improved from the previous year. Performance equals 1 if improved, 0 otherwise, so we have here categorical variable. The employee's age and income, so we have now numeric variables. And whether the employee holds a managerial position or non-managerial position, so we have a categorical variable here. So in fact, we are working on the category or the response variable is going to be the performance. It's categorical variable, and the predictor variables we have 3. 2 of them are numeric and 1 of them is categorical. But the problem is when you work on naive Bayes, we have to have categorical predictors. But we have no problem with this because we know how to deal with the numeric variables. We can convert them to categorical variables, right? We can create binning in this case because we have age and income. So first of all, we have to load some libraries. I read Excel because I would like to read the file. It's in Excel. Caret, KLAR, gains, and PROC. Some of them we have them from KNN. Some of them you have to install the packages first, then load the library. I've noticed some of students still using the import from here. If you work in a project, so this is a project, for example, chapter 12. If you work under project and your files are here, both files, the RMD file and the Excel file, there is no need to use the full path. You just use the function that we're using, XLS, read XLSX, and this is the file name, this is the sheet name. So let me run this. So this is my data. We have the performance, age, income, management. And look at the performance, look at the age, income in thousands, and we have the management 0 or 1. Again, if you look at the structure of your data, you will see that all of them are classified as numeric, and this is not something that we would like to do because we are expecting to work with the categorical variables. So we have to change these guys to be factor variables or factor. Categorical is, when we speak categorical in R, we don't want also to see character. No, we have to change character to factor. So to be recognized as categorical variable in R, we need the variables to be factors, taken levels. So that's why let's first change the performance and management to be factors. So my data, performance, just change it to be factor, as factor. Also my data, management will be changed to factor. So the question says, by the way, A says bin the age and income variables as follows. Bin age and income into 4 equal intervals. So 4 equal intervals is easy than creating these files. So in this case, we don't need to use the binning function. We just use the cut function immediately because we want to break them into 4 equal intervals. So my data, management as well. So as I said, first, let's go to my data, age, and we want to create the cut function. My data, age, we're going to do the breaks. The breaks is now 4. There is no need to use bins as we used before. Bins, we used it to create these files or percentiles or whatever. But now we just use a break, just to break them into 4 equal intervals. This is the meaning of the 4. Labels, as we did, the first part is 1, 2, 3, 4. Include lowest, some argument that we used to add, just to make sure that we include all of the data. And the right function, the right argument also is true. Repeat the same thing. When you copy paste, you have to be careful. Now this is income. This is income here. You can look at the structure of the data just to make sure that everything has been converted well. So let's look at this. So now we have factor, all of them categorical variables. Also, you can look at my data. Now we have age, income, all of them taken values as we are expecting. Now let's do the typical thing that we do is partitioning data, right? So partition the data to develop naive Bayes classification model to predict whether an employee's performance rating will improve or not when the employee works from home based on the age, income, position type. Then we're going to report accuracy, sensitivity, specificity, and precision rates for the validation data set. So let's do So let's use set seed 1. Let's have unified answers. The function that we're going to use for the partition, you can use any function, but I'm going to use a create data partition function because this one helps me to have a variety of response variable. We need the response variable to be here and there. I mean, in the train and in the validation. I don't want, if I have few cases that contains ones, for example, I don't want all of them to be in the train or in the validation. So we need to have the split of these performance or the response variable into both training and validation. So that's why I'm going to call it index as usual. So I'm just repeating what we did in the previous create data partition. My data performance is the one that you do the partitioning, 60% or 70%. Put them in list, no. After that, create the training. Let me call it train. Just my data, index, and here validation, my data, negative index. So we make sure that, so you have 120 training data and we have 80 as validation data. After that, we are going to create a 10-fold cross validation and building the model, which is again straightforward. So set seed. We're building the model on the training data, my control, train, control. The method is CV, cross validation. How many folds? Number 10. So naive Bayes fit, we're going to fit this guy, training. Performance is my response variable. Use all of the predictor variables, comma. Data is my training data. The method is called naive Bayes, NB. TR control is my control. Then let's look at the naive Bayes fit. This is exactly what we are seeing right now. So what do we have right now? We have the naive Bayes has been performed. We have 120 samples in this data set. We have 3 predictors. The data set has 2 classes. They're labeled as 0 and 1. We have cross-validation technique used, 10 folds, right? And this is the sample size for the 10 folds. And we talked about 10 folds. How does this mean? What does it mean by the 10 folds? We have 2 measures are reported, the accuracy and kappa. And the accuracy, for example, we have 75.9% with a kappa statistics 0.49%. And this becomes lower if the use kernel becomes true. I will not be commenting on this. So the accuracy rate, let's focus on the accuracy rate and just avoid talking about others. The accuracy rate is I mean, it's not bad. It's a very good accuracy rate for this model. And this model was built on the training data. And let's see the performance of this model on the validation data. So let's do this. So we are going first to create the probabilities. After that, we classify them into classes. So I'm going to call it naive Bayes class probability predict function. So we are going to plug in what? The validation data into the naive Bayes fit model that we have built, right? So we're going to plug these data have never been seen by the model into this model, and we are going to ask the model, oh, classify these performance to me. But before classifying the model and give me 0 or 1, I would like you to give me the probability, because it's, naive Bayes is about probability, right? So give me the type to be probability. And let me just explain this quickly. So NB class, let's see, what does it mean by this? So the first case in the validation set, we pass it to the model, and the model said, we are going to say 66%, the probability that this case to be classified number 1 is 66%, or the performance is better is 66%. So this case, this person will be classified as number 1. Second one, what is the probability that the second case will be classified number 1 is 42%, so that's why we will not classify this one as 1, it will be classified as 0 because the 0 is above 50%, right? The third case will be classified as 1 because this is 95%. Fourth case will be 1. This will be 0, 0, 1 because above 50%. 1, 0, 0, and so on, right? So to do the classification, we can just use naive Bayes class. which is use a predict function, the same function as is, just without specifying the probability. Just validation without specifying the probability. By itself, the function, the predict will classify these guys, and we can have a look. Oops, where is it? Look, the first case 0, second 1, 0, 1, 0, 1, 1, 0, 0, etc. Let's see the confusion matrix. The confusion matrix, how the confusion matrix does. Confusion matrix of NB class. This is the predicted values versus the actual values. The actual values. Just let's specify the positive to be 1. So if you look at the accuracy, is a little bit lower than the accuracy of the model. When we build the model on the testing, on the training values or dataset, this is a bit lower, but look at the cases, the reference, the actual, and the predictions, right? So we are correctly classified 37. It's good. It's actually high, the sensitivity here, which is, yes, it's 80%. It's 80% the sensitivity, but the specificity is a bit lower. It's about 64%, because look at this, 22 correctly classified as zeros. However, we have 34 should be 0, but we correctly were able to classify 22 of them out of 34. So we have 64% specificity, but still both of them are good numbers. They are not bad. The precision is about 75%, which is good actually. But again, to say good or bad, we need to compare these with different models, with different techniques that we may use to build such kind of model. So after that, we will be creating the performance charts. I will basically create first the table, after that the gain table, after that I'm going to plot. I use the same functions that I used in the KNN, the same thing here, the cumulative lift charts and the wise or the decile wise chart as well. But before that I have to have the gain table, so let's have the gain table, right? So the gain table, if you remember, before this we have to change the validation performance to be as a numeric, but we have to make sure that to change it as character first, then we change it to numeric, to avoid having 1 and 2s, keep them 0s and 1s, as we said before. Actually, I'm just repeating what I did in KNN validation. I will create another recording about how to read the table. It's kind of complicated, so it needs a full like 20-30 minutes to be explained. So that's why I'm gonna focus on just the table in different recording. So I'm going to just take the second, which is the ones. So we're going to build the gain tables. Gain table. So this is the gain table. We can now create the lift chart. So we have to create the lift chart and decile wise chart, right? Does the entire lift chart lie above the baseline? Let's see. What is the lift value of the liftmost bar in the decile wise lift chart? So let's build these. Again, these values you can just, these functions you can just copy them. Gain table is not there. Gains table. So this is the lift chart. It is above the baseline. Overall, yes, it is above. How good is that? How far is that from the baseline? It's not very far. I mean, the optimum one should be something like this. From here, something like this, like that. But still, it's above the random assignments for the cases. So it is above. We will be commenting and we will look at all of the performance measures and have one decent, like a coherent conclusion. Also, we can look at the decile wise lift chart. You can copy this. And again, still we have like the first 10% we have above 1, which is better than the baseline model. The second one is above 1, but still it's not really high. So in this case, we can say here, I mean, the lift of the first 10% of the observations, 10% of the observations, which is the first bar now, is about, because the question says something about the first bar. Yeah, what is the lift value for the leftmost bar in the decile wise lift chart? Yes. So this is the first bar. The lift for the first 10% of the observations is about 1.2. We can't find it here, by the way. This is the lift index. This is 1.2. 1.22, 1.11, 1.74, etc. So it's 1.2, and this means what? The top 10% of the observations selected by the model contain 1.2 times as many class 1, the target cases, as many class 1 cases as the 10% of the observations that are randomly selected. So the model is doing much better the random selection. It's 1.2 times as many class 1 cases as the 10% of the observations that are randomly selected. So it's doing better. How better? 1.2. It's not like high. It's not. If you have something like above 2 or something, 3 times as many class 1 cases, wow. 2, but this is still better than the randomly selected by the baseline model. Also, we can create the ROC curve. What is the ROC? The ROC curve, we can just, let's call it object ROC function, validation, class, probability. Let's look at the second column of this. Because the naive basic class probability has 2 columns, 0s and 1. We'll be just looking at the second one. Again, if you want to see it, just copy this, look at that one. We have 2 columns. One for the 0, one for the 1. One of them is enough because one of them is going to tell you the other one. Because if you add these guys, is 100%, right? And the same thing here, 100%, 100%. So the second one is fine. We can plot the ROC function as well, ROC object. And we can find the area under the curve, ROC object. We use these guys in KNN. So we have something nice here. We have, it performs better than the baseline model in terms of the sensitivity and specificity, because the optimum case, when we have the optimum curve, when we have this guy comes like this, from here like up to this, it's more curvy, but this is good, and the area is nice. There it could be in 70s. It's 76%. Yes, it's 76%, which is good. So the model has a good predictive performance. Sorry. So what can we say in summary? What can we summarize this? We have to summarize the idea of building these models. We have to summarize what we have found. We have to tell me a story at the end. It's not about just coding. It's about interpreting the results, comparing the results from different models, and you have to tell me how the model does. So in summary, we can say the model has moderate overall accuracy. It shows, let's say, high sensitivity and good specificity, because the sensitivity we had is about 80%, and the specificity is about 65%. And this indicates the ability to highly and correctly classify or identify the positive instances. Also, we can say the decile-wise chart show that, or the cumulative lift chart shows that the naive Bayes perform better than the baseline model. This is the baseline model, the dashed red. Also, the ROC performs better than the baseline model in terms of the sensitivity and specificity, right? And this is across all of the cutoff values, Any cutoff values that you're going to use, the model is doing well compared to the baseline model. And the AUS value, which is 67%, tells you that the model has a good predictive performance. So let me write all of this down and just to close the thing. So this is just the summary of this model, and we can tell that the model is doing all right. But again, the best thing to do is compare it with other techniques and tell which technique is going to tell you more and give you more or better predictive performance. Thank you.